That's right. It's all ultimately coming from here, so it isn't that unlike the other actor-critic model that we had, but they're computing advantage kind of differently. They're saying what we actually know from this is the value, and what we actually know from this is the action. But how can we get from that the error of the action? And the way you get the error of the action is kind of the chain rule. So we're back propagating across the policy to get the error at this point, which is really the error on the state. But by multiplying that by the advantage, which is the difference between the Q value and the policy, we arrive at an error signal for the action. That almost made sense in my head, but not quite enough. Truth is, I feel a little like I'm BSing. You sensing that? Hey, what's that? BS. There's a ASL sign for it. These are the horns. This is the tail. Okay. All right. Yeah, that's one of my favorite signs, although not necessarily appropriate. Okay, moving on. So please read through this, see if that can click for you. A, advantage, is an estimate of the advantage function given by big nasty equation. Let's parse through this equation, see if that makes sense. Do you see here, we have two gammas. So we're discounting your reward, and we're also discounting your value. But notice the discount on the reward is raised to the I power, where I is iterating from 0 to k minus 1. However, k is a constant value in a summation here, right? So this value is a one-time, discounted one time, whereas this is being discounted all along the path in which you trod. Okay? And we're subtracting from the value of, okay, let's look at this for a second. The value of s sub t plus k, this is going to be the value at the end of your path. You see that? Because t is the time you're at, k is the number of steps you took. Value of s sub t, that's the value at your beginning of your path. Okay, so we've got the difference between how good you were when you started and how good you were when you ended. Here we've got the reward that's been discounted all along the path. So for each reward you get, but it's not as good if you have to wait a long time to get the reward, right? If you have to wait for the marshmallow, it's not as awesome as the marshmallow that you get right now. Okay. Let's see. These two terms together form kind of the Bellman equation, right? Discount is reward plus discounted future estimated value. We actually know the value at the end. It's given to us right here. So we don't actually have to sum up the rewards to get it. We can just take the value at the end and add that to the rewards we get all along the way. And this together makes the Bellman equation. So this is the overarching Q value. You see that? And then if we take the Q value and subtract the value, what do we get? That's the advantage, the value of the action in the state, which is what we're calculating by the advantage. Yeah, the improvement of having taken those k steps. Yes. Yeah, so the question is, what happens if the game's over before you reach k steps? How do you deal with that? Well, essentially what you do for these equations is you just pretend that k was smaller. So if you're going to take 10 steps, but the game's over after only 6 steps, let's just pretend k was 6 for that moment. And then we can do this equation where k is 6. And then we just happen to reach the goal right on our last step, and now it all just works out. It's actually not going to affect, it's not going to hurt anything because we took fewer steps, the difference in value is also going to be smaller. And so the amount that we update is going to be proportional to the length of the path. So basically, I claim it just works out. There's not really anything we need to do except for just acknowledge that k didn't go up to 10, it only went up to 6, or whatever number it went up to. Or do they update all along the path? That is an excellent question. I don't think it actually states in this paragraph, but I can't imagine they would only update it for the one spot. Although I could be wrong. Another thing to notice is they are using neural networks to represent their tables, right? So if you only update it at periodic spots, it still generalizes, meaning it updates kind of everywhere anyway. So it might be that they don't mind updating it only at periodic intervals because then they're going to run the path a bunch more times, and so eventually it all gets trained. So it could work either way. But usually when you have information, you want to use all of it. So I bet you they iterate through it and update them all. They do have source code published online. So if somebody really, if you feel a need in your heart to know details that aren't very clear in the paper, you can dig out the code and walk through it. Not sure what else to say. The gist of it is, this is a popular algorithm, so we got to kind of look at it, and this is how far I understand it. I wish I knew whether they updated it every step or all along the way. But in some respects, I don't think it really matters because I bet you it would work either way. The best answer would be test them both, see which one performs better, pick that one. I mean, that's kind of how we solve all problems in artificial intelligence, is try it out, do an empirical study. It's a very, very empirically driven field, and has been for a very long time. Okay, one other thing I want to point out to you is this. Note, while the parameters theta of the policy theta sub v, what's the v represent? Value function. That's the critic, right? That's this one. Okay. Of the value function are shown as being separate for generality. Oh, so theta of the policy and theta v for the value. Okay. So this is the actor, this is the critic. We always share some of the parameters in practice. Little tiny sentences like that embedded in the middle of a paper are kind of, yeah, we've been describing all this theory that you wanted to hear, but in truth, we really coded it up this way. You got to catch little details like that, because in reality, that makes a huge difference. Here's what's going on. You see how we've got these two functions, and they both take the same inputs. The actor has state feeding in. The critic has state feeding in. The only difference is they have different outputs. So let's move these like this. And it's more like, I apologize for my terrible figures, but it's kind of like state feeds into this and state feeds into this. And the one that produces actions is the policy, and the one that produces value, we'll call that V for now. Is that what they called it in the paper? Mm-hmm. Okay. The one that produces value is the critic. And it turns out that most of this is the same thing, because state in this algorithm is a screenshot, right? Now, screenshots are very big. Imagine you have a 640 by 480 pixel screen. That's how big our screens were back in the days of Windows 3.1. 640 times 480 times 3 channels gives us 900,000 numbers that are all coming in from a tiny little screenshot. Of course, it's much bigger than that now, right? It's like, what is the resolution of my screen? 1366 by 768. 1366 times 768. Okay, you've got at least 3 million values feeding into this thing from just a screenshot. Now, of course, if you're doing Atari 2600, you're back in the old resolution days, but it's still a lot of numbers is the point. And crunching all those numbers is going to be expensive. They have convolutional layers, which are really good at digesting images. So if you work with images, you probably want to use convolutional layers. What they did is they essentially took most of the layers and common coded them. So it's kind of more like this, where they're really training one great big neural network, and it just happens that in the very last layer, here I'll feed it out a little bit, they're kind of separating into a tiny little layer that can compute whether we're doing value or whether we're doing actions. And this is kind of an interesting concept because it facilitates what we call transfer learning. Have you ever heard of transfer learning? The idea is, if you're good at task A, are you also good at task B? Well, we're using the same network architecture to compute actions as we are to compute values. So while these output layers of the neural networks are going to differ greatly, the inputs can't differ. They're forced to be the same thing. So what does that force the neural network to do? I don't know, but it's weird and interesting. It forces this input to learn the common language of what's going on. Do you see how that essentially forces it to become like these mirror neurons? It says to it, hey, you need to really figure out meaning in this because you're going to have to use that meaning to compute, to evaluate the value of things, and you're going to have to use it to compute the action that I'm supposed to perform. And because you're doing two jobs with the same architecture, it forces this to become significant and meaningful. That's the idea behind transfer learning. Well, it's one of many ways to do transfer learning with neural networks. Okay, also, this constitutes 99.9% of all the weights in the neural network that they actually train. These are trained really rapidly, and they don't contain that many weights. Because these are processing images, it takes a whole lot of weights that are all being tuned to digest those images. So this is going to digest the images to figure out what's going on, hopefully forming mirror neurons or some equivalent thereunto, from which these functions learn to compute what we really need to compute. And whether we're updating the action or the value, most of the weights are being updated the same way. We typically use convolutional neural network that has one softmax output for the policy and one linear output for the value function. So in other words, this happens to be a softmax layer, if you know what that is. If you don't, that's okay. I haven't taught it in this class. But a softmax layer is a layer that is constrained to output values between 0 and 1, and is constrained so that they sum to 1. It's basically for doing probabilities. So remember, we choose the actions from a probability distribution. On the other hand, the value, they use a linear layer here, which just combines the values in a linear way and outputs things. So they don't have the problem of, remember your Q values had to range between 0 and 1 so that my neural net could handle it. They don't have that problem because the linear layer can hit any range you want. So they've thought this through. Okay, we also found that adding the entropy of the policy to the objective function improved exploration. So yeah, we did some tricks that actually were shown empirically to work. The gradient of the full objective function, including the entropy regularization term with, is this. So now that we've gone through all this theory and told you how we're doing it, this is what we really did in code, which differs from what they actually said they were going to do. And then there's the paper. Okay. One thing I'd encourage you to do is go to YouTube and Google for some of the things that A3C has. A3Q? It's A3C. I don't know where I got a Q from. I must have mistyped there. Google for some of the things it's been doing lately. They've actually got this thing playing modern video games and beating professional players. And it's pretty cool to watch it play. And it's pretty cool to watch people that are unconquerable on the professional playing field just throw in the towel and say, I give up, this machine's insane. Watching machines cream people just is kind of satisfying to me in ways that are hard to express because my whole career is kind of built around it. But yeah, the machines are taking over. You're all doomed.